All right, so today we're going to be talking about gas behavior. So, just understanding what is actually happening with gases to help us explain kind of why some of our calculations end up being what they end up. So we want to revisit just again what is pressure. Pressure is a force that the gas molecules are exerting when they run into a surface, whether it be a wall, whether it be any kind of container or your lungs. Anytime a gas particle, anytime anything hits something, it's going to exert pressure. Now, in terms of what you need to know, is we want to look at how pressure is affected by changing these different things. And ultimately, it's always going to come down to how does this thing, whatever it is we're doing, affect the number of collisions? Because that's what pressure is. It's the result of a collision. So if we can make collisions go up, or if we can make collisions go down, that's going to affect the pressure exerted. So obviously here, as we look at changing the number of molecules, think of blowing up a balloon. If you put more molecules into the container, the pressure is going to increase because you have more collisions. Pressure and volume. What if we make the container bigger? Well, if we make the container bigger, then it's going to take longer for the molecules to hit the container. They have a further distance to travel, and so as our volume increases, the amount of space that is taken that our container takes up is increased, then pressure has to go down because the molecules have to travel further. Temperature. In order to understand how temperature affects pressure, we have to understand what temperature is. Temperature is an average of the kinetic energy of a molecule. It's the energy of motion. It's how fast molecules are moving. So, as we make things hotter, that means that the motion of the molecules is going faster. So, as this relates, if all of the molecules are all of a sudden moving faster, then you're going to have more collisions, and that means your pressure is going to increase. So, not only because of the moving faster does the number of collisions increase, but also the energy at which these collisions happen also increases. Think about just walking down the hall and bumping into somebody versus sprinting down the hall and hitting someone. There's going to be a lot more energy there. So temperature goes up, molecules move faster, pressure goes faster. Increases. Now, all of this resides in this idea of kinetic molecular theory. It's just a theory that allows us to explain how gas molecules work and why they do the things that they do. These are the main assumptions of kinetic molecular theory. You do need to know all of these, so you're going to want to pause the video here and put these down into your notes. But basically, it's just a set of facts that gas molecules are always in motion, and the degree of their motion is represented by temperature. The molecules are far apart so that they don't really interact with each other. And that because they're so far apart, we can think of the volume of the gas particles so small compared to the volume itself of the container that we can kind of ignore the volume of the molecule, right? Think about how much space you alone take up in the activity center. The size of the activity center compared to the size of you, we can kind of ignore the volume that you take up. That's kind of what this is saying. Now, there is a problem with kinetic molecular theory that even though it does allow us to explain basically all of our observations that we might have about a gas, there are certain situations where it doesn't quite work because we deal with real things. And so there are a couple of assumptions of this theory that it's not entirely true in certain situations. So, for example, gas particles don't bounce away perfectly. There is energy transferred from one particle to the other. Granted, it's extremely small, but in certain environments, in certain lab situations, you can't always ignore that. And the fact that gas particles are actual real things. And so, generally, we can ignore those to explain why gases behave, but in some situations, you can't, because you can't ignore their volume because they do take up space. And you want to know both of those for the test. The last couple things are just definition wise. So we have effusion, and this is where gas escapes from a tiny hole in the container. This is why a balloon on your birthday after a couple days is a little bit smaller, because the gas just naturally leaks out over time because the balloon surface is not whole. There are little tiny holes where the gas can escape. And the last one is diffusion. So this is gas moving across a space. So this is the reason why when an overzealous teenager walks into the room wearing too much Axe body spray, everyone can smell it, because the gas just eventually, due to its random motion, is going to fill up the container, which is why in this case is the room. These other things you don't really need to know for the test. This is just more FYI that we can think of the mass of particles. So as particles get bigger, things move slower. So effusion is not going to happen as quickly, and diffusion is not going to happen as quickly. Just because of the extra mass, things just move slower. And that's it.